everyone. Today I'm going to talk a little bit about hyperparameter tuning. Last week I quickly introduced this topic, and now I want to try to uh, explain again the example that I quickly covered last week. Okay, so basically, as I was mentioning in the last lecture, you can have a look and check the slides in Canvas. But let me just quickly describe the idea of hyperparameter tuning. Okay, so basically when we want to build the model, the machine learning model, the supervised learning model, and in particular, for example, with decision trees, well, basically the first step is that we need to try to explore to compute the entropy of all the features, all the attributes, and then we are going to be using, for example, the entropy. We compute the entropy, the classification error, or the Gini index of all the attributes that we have uh, for my problem. And then we are going to use the best one, for example, the one with the minimum entropy, one with the maximum information gain. Okay, so basically, for example, here, let's say that this is the best one that we are going to be using for this example, and then we are going to grow the tree. Okay, so basically we have two alternatives, and then we are going to be choosing again the next best attribute, and so on and so forth. The question here is when we want to stop growing the tree. Okay, so and there are multiple parameters that we need to identify the value for these parameters that we need to identify. Okay, for example, one of the critical parameters, the most important parameters that we have in decision trees is the mean split parameter. Okay, so let's say that at the very beginning, we are going to have a number of samples. Let's say these are the samples that we have in the training set. And for example, we have 100 samples. So basically, we're going to split, we're going to grow the tree, and then we can choose to go with um, 60 samples. Let's say that we have 60 samples if we split the tree in this way. If we go in this direction, in the left, and we have 40 samples in the right direction of the tree. And then we keep going. And for example, in this particular case, we have this particular example here. We have this node with only one sample. So at that point, we cannot grow the tree anymore. That is not going to make any sense to continue growing the tree. So we have to stop here. So basically, in this case, we're going to be saying that the mean split number is equal to 2 because we need at least two samples in order to grow the tree. But we can change. There is no fixed rule to say, okay, which one is the best value. Unfortunately, we don't have this magic number in order to find the mean split. And this parameter is actually going to change from one problem to another one. There are other problems, for example, with different parameters. Okay, so basically this is one of the parameters that we can use. For example, if here we can continue growing this sample with 40, then we can keep going the tree, we can keep growing the tree. But we can say that, for example, we want to stop if we have we can say that we are going to grow the tree if we have more than 40 samples, more than 40 examples. So in that case, for example, if we say that we need more than 40 samples, then we are not going to be growing the tree in some particular nodes. Okay. Now, for example, let me have a look at this example. Okay, so basically, this is just basically here we're just building a model, a naive-based model for the wine data set. This data set, as far as I remember, is available in Canvas, and then you can try to explore this data set in the same way. Okay, so basically here, this is an example that we have seen in the past. Basically, we are in this line, we're just telling the library that we're going to be using decision trees. Now we are just getting the data set from the file. Now we are telling that this particular attribute is going to be the target feature. We're telling the library that we're going to be using this data set. And now we're going to be telling the library that we're going to be using cross validation. Okay. and the value for cross validation is going to be 10. And you can try to explore different values. Now we are going to be telling the system, okay, build the decision trees for this particular example using 10 for cross validation. Okay, in this particular case, we are not identifying, we are not using we are using the default parameters that they have in the library. Typically, well, always we have default values for the parameters, and but those values for the parameters are most likely not going to be good enough for your particular application. Okay, so for example here, if we run this, if we execute this small program, then we are going to be seeing, I'm going to put this program in Canvas, so you can have a look and you can play with this. Remember that here you have to indicate the location of the file, and other than that, we don't have anything. I'm also indicating the random seed in order to be able to replicate the experiment and to get the same accuracy. So basically, this is the accuracy that we have, the mean accuracy for 10 for cross validation. Sometimes you get you can also have a look at the runtime. This is a small example, so we're not going to be seeing, this is not going to take a lot of time. In this particular case, the default parameter configurations are going to be using 89% of accuracy, but we can change this if we want, if we start playing with different parameters, okay? So for example, if we say mean split, then we can just change these values. Okay, for example, I can say that that we need to have at least 20 samples in order to grow a tree. Okay, basically this, in this particular case, is a little bit worse than for this random seed. Of course, if we change the random seed, then we are going to be seeing different numbers. It's going to be worse than the default parameters, but we can start changing this. For example, I'm going to be using 5, and in this case, we get a different combination. Now we can have other parameters, for example, maximum number of levels that we can have. Then we say, for example, 4. This I'm just trying to play with these numbers in order to see the performance. And now, for example, if we want to change the method that we use to define the best attribute, for example, we can say parents equals to split equals to entropy. Then we are going to be using the entropy, and we can also use, for example, the error, the misclassification error, and for example here is 89%, or we can just, so as you can see, if we change the parameters, we will be getting different performances, different accuracies. At the very end, what we want to get is the method that is giving me the best performance, accuracy, or depending on your metric. You can also start playing with the metrics. You can use recall, you can use precision, or different alternatives. Okay, so basically this is, of course, one alternative is that I start manually trying to write all the possible parameter configurations, or I can even write my own code in order to find all the parameter configurations. Okay, but this library is going to provide a functionality in order to automatically do this hyperparameter tuning alternatives. Okay, for example, here we have an example that is going to be using the library in order to create, to get the best parameters, in order to identify the parameters that we want to fine tune. Okay, so basically here at the very beginning, I'm just trying to get all the parameters, and just printing here the number of parameters that we have for this particular method. This is nothing really different to what I was saying before. Don't forget to change here the location of your file. And basically, if you want to start playing with all the parameters and these hyperparameter tuning options, what we have to do is that we have to use this function called main_parent_set. This is going to tell the system the parameters that we want to start playing with. Okay, basically, if you have integer values, you can use main_integer_parameter, and then it's going to be indicating the parameter that we will be exploring. mean split. This is telling me the minimum value that we want to use for all the combinations. So we are going to be, in this example, we are going to be saying that the minimum value is going to be 1, the maximum value is going to be 100. So basically what the program is going to be doing is that it's going to be trying mean split equals 1, and then mean split equals 2, mean split equals 3, mean split equals 4, and so on and so forth until we get to mean split equals to 100. Okay, so this is for the first one. The same goes for the second one, and then we have the CP parameter, which is a continuous variable. Okay, so in this particular case, we need to identify the the values for this for the parameter tuning set. So basically, we are going to create a sequence of variables. So it's going to be a sequence starting from this number up to this number, and this is how we're going to be increasing. Okay, so for example, what the library is going to be doing internally is going to say, is going to try all these combinations. Means split equals to 1, and then that equals to 2, and CP equals to 0.1. This is 1, and then we're going to be changing another one. I'm not writing all the code for the library, but this is just to give you an idea of what's happening inside. 3, 5, and then it's going to be trying 1, and then exploring 3, and so on and so forth. Basically, it's going to try all possible, it's going to try different combinations depending on the method that you use. If you use grid search, then you will be trying all possible combinations, and if you use random search, it's going to be trying just random options. Okay, basically, depending on the one that you want to use, you are going to activate, you are going to be using one or the other one. Okay, basically here I'm commenting random search, so basically I'm going to be using grid search, and here I'm going to be, depending on the one that we want to use, I'm only using cross-validation, and k, the value is going to be 3 in this toy example, but you can try different variables. And now I'm going to be tuning in this line, I'm going to be doing the hyperparameter tuning for this particular model. Okay, so basically this is just telling the system, this is the parameter set, depending on the values that I define beforehand. If you have more parameters, if you want to fine tune other parameters, then you can just include those parameters here in the parameter set. Basically, we can just try this and then have a quick look at this. Okay, as you can see, this is trying to explore all potential configurations. This is what we are doing here. Now, how can we get all these numbers that we have in here? Okay, for example, these are the optimal parameters that we found for this particular example with these particular conditions. Basically, split equals to 1, maximum number of levels 23, CP1 equals to 0.005, and this is going to be the accuracy. As we can see, this accuracy is better than the one we have, for example, by default, and the few parameter configurations that we explored a few minutes ago. If we want to get this, basically we can just use res, which is the output of tune parameters, and then you will be seeing all this information. Now, if I want to get the values of these particular variables, all you have to do is to get the x value of the x value of the res, the output of tune params, and then you get all the parameters that you defined beforehand. Okay, for example, let's say that we want to get the CP parameter, so it's going to be 0.0045, this one here, but we can also try to get the max depth. For example, just max depth, and then we get this one, and so on and so forth. And if we want to access the accuracy, all we have to do is y, and then we get the accuracy of this particular example. Okay, I can also change this, but as you can see, it's going to take more time because I'm trying to change the configurations that we have. Of course, in this particular case, it's going to take a lot of time because as you can, it's going to try to increase the number of experiments that we are going to be doing. Okay, let me just quickly reduce this. Yeah, I was talking about grid search and random search, but we have a very large number of alternatives in order to do hyperparameter tuning. I could be talking about this for one entire module about all the techniques that we have. But unfortunately, I don't have enough. I don't have a lot of time for that. But another very popular technique, I do like this approach. Greedy search, well, it's a little bit more complex than what I'm going to quickly explain today, but you can get an idea. Okay, so basically, greedy search is a kind of meta-heuristic approach in which we are going to be starting with a particular parameter configuration, and then we are going to be exploring the neighbors of that particular parameter. We go and then we move to the best neighbor, and then we repeat the best neighbor is the one that improves the accuracy, and then we are going to be choosing, and then we move to that neighbor, and then we explore the best neighbor, and then we keep going. Okay, for example, let's say that we have the decision trees example, and then we have the two parameters that we have, I mean, split these two parameters, we can have more, and the maximum number of levels that we have. Let's say that we have all these values for mini split and all these values for the maximum number of levels, and these are all the parameter configurations. Of course, I'm only going to try a small number because otherwise it's going to be a quite big example. Okay, so basically the first step is that we need to start with a predefined parameter configuration. We can start, for example, with the default parameters configurations that we have in the library, or we can just take a random starting point. And then we're going to perform a greedy move. Basically, what we're going to be doing is that we're going to be changing the value for only one of the two parameters, or only one of all the parameters that we have. Only one, for example, if we are in this node, basically we can only explore this one, this one, this one, and this one, and then we're going to be moving to the best value. And then we move to that value, and then we repeat the process again and again. Okay, for example, in this particular case, let's assume that we're going to be starting here, and then we perform cross validation and so on and so forth for this parameter configuration, and then we get 70%. So basically, we're going to be exploring the neighbors, which are going to be, basically, this is one of the neighbors. Remember that the way that we're using here, this basic approach, is just allowing the change of one parameter at a time. Okay, for example, if we are here, we are going to be changing only the mean split. We can increase that value 1 or decrease that value 1, or we can increase the maximum number of levels or decrease the number of levels. But according to this definition, we cannot change both at the same time. For example, this is not a valid neighbor that we call. Okay, so based on this, basically, okay, we have all these neighbors. So basically, we're going to be moving to this neighbor that we have here, which is the one that provides 80% accuracy. It's improving the parameter configuration, the accuracy. Okay, so basically we select that neighbor, and now we repeat the same process. I just have this in gray in order to identify the ones that we already explored. Okay, so basically here we repeat the same process, exploring the neighbors. For example, here in this toy example, this is decreasing the performance quite a lot. This one is also decreasing the performance quite a lot, and this one is increasing the accuracy in 1 unit. So basically we are going to be moving to that particular parameter configuration. And then we repeat the same process again. Now we have 73%, 83%, 65%. So in this case, now we are going to be moving to this parameter configuration. And now we repeat the same process. Now we have 87%, and so on and so forth. Okay, and then we repeat the same process until we cannot improve anymore. So at this point, we have to stop, and we have to, that's going to be the solution if we try a basic greedy search approach. Now, as you can see here in the greedy search approach, there is a lot of number of parameters that we are not exploring. Okay, all these parameters we are not exploring, and that could be a problem. Okay, because probably this is far from the optimal solution. So what we can try to do is to combine greedy search with restarts. Basically, what we're going to be doing is that once we find the solution that we cannot improve anymore, what we are going to be doing is that we are going to be changing the starting point, which is a different starting point, and then we repeat the same process, and then we are going to be repeating that a number of times. And then, of course, we are going to be using the best solution, the best overall solution. Okay, so basically there are a lot, I was saying, a very large number of options for hyperparameter tuning. This is a very important area in data mining and supervised learning. We have grid search. The grid search and random search are two quite popular ones because they're quite easy to implement and they are available in almost all uh, libraries that we have for the topic. And then we have greedy search, we have greedy search with restarts, genetic algorithms, that's also another very popular alternative. Uh, but that is a huge area that we are not going to cover. Estimation of distribution of algorithms, Bayesian optimization. As far as I know, this is currently a state of the art. One of the best alternatives that we have is quite extensive, but I'm not going to be talking about that. If you want, you can have a look at the library. They provide state of the art implementations of this Bayesian optimization. This is not available, as far as I know, it's not available in our machine learning tools. Okay. Now in order to finish this video, I'm going to talk a little bit about the lab of this week. The idea is that we're going to be working in a lab about hyperparameter tuning. We will be using the libraries that I have been using today for this job. And basically, this is the description of the lab. We will be using the same data set that we were using a couple of weeks ago about the Titanic data set. This is available in Canvas in week 6, as you can have a look here. Basically, we have week 6, and then basically we have the training set and the testing set. Remember that if you want to evaluate the accuracy of the testing set, we don't have the actual labels, so you can submit your answer in Kaggle, and then you will get the accuracy. They will give you the accuracy of your model. Okay, so basically this is just generic information about the data set. And then the idea is that you're going to be using as a baseline, you will be using your solution that you have from before. Basically, my solution is also available in Canvas. If you have any problem with that, please let me know. And basically here we're going to be using phi cross validation. If you want to play with different values, but I recommend to use phi because you will be seeing that it's going to take a lot of time, in particular for random forests. And the idea is that we're going to be trying to get the default parameter, the performance with the default parameters for decision trees. If you want to use decision trees, basically you will be using this option. If you will be using the k-nearest neighbor, you will be using this option. And if you want to use random forest, you will be using this option. Okay, this is just with the default parameters. Now the idea is that we are going to be using grid search in order to try to find the optimal hyperparameter values, and then we will be playing with some hyperparameters. Okay, for example, for decision trees, we are going to be using mean split and the maximum number of levels and the CP value. Okay, for the k-nearest neighbor, we are only going to be playing with these two parameters. For random forest, we are going to be playing with these three parameters. Okay, so if you want, you can certainly play with the parameters. You can go from You can try to have more trees if you want 100, but be careful because this is going to increase the time. It's going to take important amount of time in order to find the solution. Okay, so basically what you have to do, more or less, this is just an idea from your lab from a couple of weeks before. Your accuracy should be more or less 74%, more or less. And then basically, hopefully with this hyperparameter tuning, you will be able to improve that probably up to 77%. Okay, so basically this is the idea of this. And basically something important that you have to do here is that you will be using, for example, this is your training set and this is your testing set, and what you have to do is basically try to use this training set in order to get the optimal hyperparameters, and then you build your model with those. In the testing set, you build your model with these values. Remember that if you want to get those values, all you have to do is um, all you have to do is to use the output of the tune parameters function, and then you can just tune x and the name of the parameter. Okay, mean split, match that, and so on and so forth. And you will be getting the maximum that. Okay, so try my advice is to try to create, for example, one function for pre-processing your data set, another function for building your model with your basic model with decision trees, another function for building your model with hyperparameter tuning, and then creating the model for and then creating and then getting creating the model with the optimal parameters and computing the predictions. And then that solution, the predictions, you have to submit that in Kaggle in order to get the, the accuracy. Okay, so that's basically all I wanted to say for today. Something a little additional important things is that basically if you have any question, please try to use the discussion board. So basically you go into discussions and then you create new discussion and you formulate your questions. Please try to use these discussions because it's going to be useful for everyone. So probably another student is going to have a similar question in the future, and that's going to be useful for all of us. Okay, thank you very much. And hopefully I will try to create another video next week, hopefully talking about clustering techniques. Most likely we'll be talking about the the K-means algorithm, and the K-means algorithm. Those are two very popular and supervised learning techniques. Thank you very much.